In this lesson, we're going to be talking about some applications of vectors. So as we've already read, velocity is speed in a direction and therefore can be represented by a vector. Our first example is going to be involving an airplane and some bearings. You should have already read about bearings and done a few examples involving bearings. So just to remind you of a couple of things, a bearing is measured from the north in a clockwise direction, and our position vectors are measured from the positive x-axis in a counterclockwise direction. So there is a lot going on here, and you do have to keep track of a lot of different things. So our first example here says an airplane is flying on a bearing of 300 degrees at 450 kilometers per hour. Express the velocity of the plane in component form, so what you just watched in the last lesson, and include a diagram. So in this example, I am specifically asking you to include a diagram, but even if I don't, it's a really good idea to draw one and make sure that your answer makes sense compared to the diagram, and just check your work as you go. So I'm always going to say I want you to include a diagram even if I don't specifically ask for it. So I'm just going to start this example out by drawing this diagram. So I have my airplane flying on a bearing of 300 degrees. So this means starting at north, we have to go clockwise 300 degrees. So I've got 90, 180, 270, 300. That means that what I'm going to have left here is 60 degrees. Now, if I want to try and get my direction angle, remember, this is starting at my positive x-axis and going counterclockwise. I have the 90 from quadrant 1 plus the 60 here. So I have 90 plus 60, 150 degrees. Now that I have my diagram and I have my angles, I can start expressing this velocity in component form. So I am going to call this v, vector v. So I do know from the question that the magnitude of vector v is equal to 450. It tells me that it is traveling at 450 kilometers per hour. Now, just to recall, if I'm trying to put this in component form, I have that vector v is equal to the magnitude of v cos theta, the magnitude of v sine theta. I did all of the hard work already. I know the magnitude of v is 450, and I know that my theta, or my angle, is 150 because I figured it out right here. So really, what I'm getting is that v is equal to 450 cos 150, and then 450 sine 150. And then if I plug that into my calculator, 450 cos 150 is negative 390. And then 450 sine 150 is 225. Now here is a really good time for me to go back and double check. Does this make sense? I would have negative 390 in the x and a positive 225 in the y, and things definitely look good there. Those numbers make sense. All right, so for example 2, a small aircraft is flying on a heading of 330 degrees at a constant speed of 150 kilometers per hour. I'm going to call this vector right here vector P for plane. Notice that it is 330 degrees a heading, so we're starting from north and going clockwise 330 degrees. I'm going to label this blue vector right here, vector W for wind. The wind is blowing on a bearing of 85 degrees with a speed of 40 kilometers per hour. Determine the actual speed and direction of the aircraft relative to the ground. Include a diagram. So I have this diagram here. All of my angles and everything are put in, I'm basically going to take these two vectors that I have drawn and I'm going to redraw them over here just so that you can see maybe without so much stuff going on. So I've got vector P right here, and then I have vector W right here, so the plane and the wind. Now, what I do know is that the angle between these two vectors, if the aircraft is flying on a heading of 330 degrees, that means that this little angle right here is 30. 360 minus 330, and we know that the wind is blowing on a bearing of 85. So this angle right in here that I'm going to call theta is the 30 plus the 85. So this means that my theta is 115 degrees. Now, if I continue this, I have these two vectors that are tail to tail. So I'm going to draw this parallelogram here. Remember, tail to tail means the parallelogram. I can see that my resultant would be right here. So I know that theta is 115, and then the other thing that I know this green theta, I'll call it theta 2 up here, and I know that theta 2 is going to be 65 degrees, and I know that because of the C pattern. So those two angles right there form a C, and so they must add up to 180. Next, I'm going to add in all of the extra information that I know. So I know that my plane is flying at a speed of 150 kilometers per hour. Put that in red. And then in blue, I know that the wind is blowing with a speed of 40 kilometers per hour. Now, because this is a parallelogram, I know that that also means that this is also 40 kilometers per hour, and this side length over here is 115 kilometers per hour. We are still trying to solve for this resultant in here, and that's why it was so important for us to get the theta 2 at the top there, because then we will be able to use that triangle to solve for the resultant. If we only had the angle in the bottom, our original theta, the 115, we don't know how much of that 115 actually belongs in the bottom part of the triangle and what part belongs in the top. Alright, so I'm going to go ahead and I'm just going to draw just another version of this triangle. So I know that this length is 150 kilometers per hour. I know that this vector, it's kind of long, this vector is 40, and 40, I know that I am looking for this resultant vector right here, and that this angle at the top is 65. So I am going to be using the cosine law. I have two sides and a contained angle, so I will set that up. Now I'm not going to write out the full formula for you. I'm just going to start plugging in numbers. If writing out the formula helps you, then feel free to do that. I have the absolute value of r squared is equal to 40 squared plus 150 squared minus 2 times 40 times 150 cos of 65. Now again, this is just the cosine law. I'm going to go ahead and simplify this a little bit more. So 40 squared plus 150 squared is 24,100 minus 2 times 40 times 150 is 1,200 cos of 65. The absolute value of r squared is 19,028.58086. And then if I go ahead and take the square root of that, it's going to be approximately 138 kilometers per hour. Not only do I want the speed of this aircraft, I want the direction as well. So what I'm trying to figure out is this angle right here. I highlighted it yellow in this diagram. It's a little bit hard to see. I'm going to call this angle gamma. You can call it theta 3, whatever you want. Since I know all three sides in this triangle and one of the angles, I can use the sine law. So I'll do that in yellow down here. So I have sine of gamma over its opposite length. So 40 is equal to sine of my theta 2, which was 65, over its opposite length, which was the resultant that I just solved for. So cross multiply, and I'm going to get 15 degrees. Our original plane, if you remember, had a heading of 330 degrees. And so what we just solved for is a shift to the right. So where the resultant, because of the wind, has been moved 15 degrees. So if our original heading was 330 and we add the 15, that means that our plane is now going to have a bearing of 345 degrees. And therefore the plane's actual speed relative to the ground is 138 kilometers per hour on a bearing of 345 degrees.